Hello guys, welcome to this video. So we are gonna go discussing about this training and sampling algorithms. In the previous two video, we understand the reverse diffusions and forward diffusion, and this is time to understand the algorithms they have proposed. So this is the training algorithms for this diffusion model, and this is the sampling algorithm, and this is the the graphical look of the diffusion model. So and we are here we have these three distributions. So if I can map it, so these are three distribution we have. P, no, this is not a P, but this is Q. Actually, this is Q of xt minus 1 given xt. This is actual, this is a forward process. So forward process is start with a clean image, add Gaussian noise iteratively, and make it undistinguishable from the uh, and which will be come from this distribution. So normal distribution, standard normal distribution, it will be the sample from the standard normal distribution. We iteratively, if we add iterative noise, our sample will be gone into this distribution, turn into this distribution, and the forward process is given by, so given by this q of xt given by xt minus 1. So it has this form u of xt given xt minus 1 will have this form. So it will be from Gaussian, and this is xt, and we're going to be sampling from a distribution which have mute. So no, this is not that, but this will be e to the power of 1 minus 1 minus beta t of 1 minus beta t of xt minus 1, and we're going to be adding Gaussian noise, so beta I. So this is the forward process. This distribution defined by this distribution. This is xt. So this is our this transition Gaussian transition distributions, and after that we have p theta of xt minus 1 given xt, and other is q theta and other is we have q of xt minus 1 xt, and let's have this form. It will be from this distribution which we're gonna get xt minus 1, and this it has this mean and this variance. So we are gonna use neural network theta, yeah, xt, and we are also having this theta xt minus. This will be the this distribution, and q will be the, if you this is interactable, and if you condition on x0, we can find this, and this will be mu tilt. Here this will have the mu tilt and beta tilt, or this is the mean, and this is the variance of this distribution. So this will be, and let's understand some of the notation which you are using here. So we are, so 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 we are given a sample. So we are given a sample. So sample of data, sample means a data sets. We have given a data set, given us, we have a data set, and from a certain distribution q of x0, we have data sets, and in within the data set we have samples which lie within this data distributions, and we are interested in learning a model distribution, a model with our neural networks p theta of x0, and that will approximate this data distribution in which our sample lies, and which distribution this p theta is easy to sample from. denoising probabilistic model given by these two paper are the latent variable model of the form. So if you write this p theta of x0, it will be the integrations, and we are going from x, and this is the joint of x joint of the we're gonna go from going from the um, x0 to t, and if we integrate this we're gonna go get our model distribution, and this is the p this joint distribution will look like this. If we expand this, so it will have this form, and there are what are the intermediates, this xt minus 1 xt x1 x3, these are the latent variables, so are the latent variables which are not real image, but are latent variable in the sample space as x0. The parameters theta, so we want to learn this theta s- to fit the, so we want the parameters are learned to fit the data distribution q of x0 by minimizing this bound, so it's variational lower bound, so we are maximizing this bound, and we are able to fit the the data distribution q of x0 by the by our p theta of x0. So this is the intuition, this is the idea of the diffusion model, and we have we have three conditionals, so conditional distribution, and we have to learn this, so not we doesn't have to we learn have this only this, so this p theta of xt minus 1 given xt. This is the forward process. This is the forward process which take less noisy image, add noise, and make it more noisier. And this is the actual reverse. This is the actual reverse conditional, which is interactable. Mm, and we want to approximate this interactable quantity with this p theta of xt minus 1 by this is our neural network. So it will approximate, or it will approximate this distribution, and which is this distribution, and if you condition on x0, we can calculate this value, but it will not use in our when we are doing sampling or when we are removing the noise. So this is just for it is helpful for our model training, and for our making our training objective. And let's look at the algorithm part. So let's move into the training part of it. So for the training, we sample some data, arbitrary data set is data, just any sample from this distribution q of x0, which is we will just take some images from our data set, and we'll also sample time step uniformly, and we'll sample noise from this distribution, it's a normal distribution, and we apply the we take the gradient descent step on this quantity here. And so what this quantity is, this is the epsilon theta, and this term is actually xt, this term is xt. So and this is time step t, this is time step, so this is time step, and if you can observe it, so we are passing this two quantity and getting the predicted noise, so we are predicting the noise giving this two quantity, this xt image, and we're also giving this much noisy image, this much noisy image we are giving, and time step we are giving, and forcing the model, and forcing the model to predict a good value of this epsilon, and this epsilon theta denote the neural network, and we're going to subtract it from the original noise that was added at this time step t. So this will model will gonna predict the noise, and we'll subtract the original noise, and we'll try to minimize this. So this loss we're gonna minimize this, and we're gonna find the optimal value of this theta, which will minimize this noise. And why we are predicting noise? So this is our actually a reverse process here. So we first of all we add noise iteratively for 1,000 steps. We are taking time step 1,000, so we will add we'll slowly destroy the structure of the data from time step 0 to time to x0 to xt, which is nearly 1,000 we are taking, and we will gradually destroy the structured data. And when you reach xt, our data will be completely pure Gaussians, which has of Gaussians of zero mean and one and unit variance. And so, and we're gonna go predict this noise added at each time step. In a 100 time step, we're gonna go need this epsilon theta 100 times, 100 different epsilon theta. But this 100, if you have 1,000 time steps, so epsilon theta will predict. We are giving also time step t, so time step is also needed. So for that, for a specific t, for a specific t, we have one this epsilon theta, which will predict the noise for us. And so, and we, first of all, if you are in a 100 time steps, so can I draw? So this is your xt. This is xt minus one. So in the forward processes, you go from the less noisy to noisy image. So and you want to, we are doing this. So we are predicting. So we are giving this image, and we are also giving this time step, and we want to predict how much noise is added from here to here, so that how many noise this step has. So and we want to predict this noise what was added at that time step. So time step t, so it will give the how much noise is added at this time step t, and we are also giving time step. So it will gonna go say that in this step, in this time step t, this much amount of noise was added. So if we remove this noise, we will get the original data. Not original data, but the previous the data which the data we're gonna subtract some noise something beta t. How much this is not also alpha bar t. So which is a how much we destroy the how much we add the noise. So it will gonna go give us it will give us the noise how added at this time step, and we're gonna subtract it from the previous one, and we'll get cleaner image. And we want to minimize this so that this quantity will becomes equal and our loss become minimum. And we'll do until we converge to, for the sampling algorithm. They first of all we're gonna go do sample some 2D vectors. 2D this vector, 2D vector, two-dimensional vector, which is a grid of pixel, which is images. So and it belongs, each pixel value belong to this distributions. And after that we're gonna go apply this for loop, isn't it? From this last step to we're gonna go do to up to this one step, we're gonna first of all sample some noise. Sample the noise. If you are not at we're gonna go sample the noise in all step except t is equal to t is less than one. So t is this is greater than one. So if our t become less than one, we gonna go not sampling this noise. But if you are greater than t, this if your t is greater than one, we gonna go sample this noise and gonna go why I'm adding noise. I'm doing samplings. So this seem a little bit of counterintuitive because we are already sampling this 2D vector. Is also a noise. It's from same distribution. This is the xt. I think if you have read the GAN, so this is just same as sampling from the GAN also, but just leave it there. I think this is just we are just sampling xt, and after that, what you're doing, you are going into this for loop, and this is the iterative process. So you are using for loop here, and you are sampling some noise, this z, and you are you are sampling greater when time step is greater than one, you're gonna go sampling this z. If you are in a time step less than one, you will gonna go you will not gonna go sample this quantity here, and you're gonna go put z as 0. And what you're doing here, this is the main sampling algorithm here. So this thing is called Langevin dynamics, or not Langevin sampling. So this is Langevin sampling. And what we are doing here, so this is our neural network, guys. This is the the image at time step t, and these are some coefficients, some scaling coefficients, and we're adding this Gaussian noise. So you can see here. So if we reach time step is equal to 1, in the last time step we're not gonna go add this noise. We're not going to add this noise. And why we are adding noise, so I want to tell you. So first of all, what you're doing just for to understand this. So take this xt, which is the time at your current steps, you want to get this xt minus 1. You give the model xt and this noisy image, you give this noisy image and get less noisy image, less noisy image. So less noisy image. So if I can just write it, so just listen my words if it doesn't understand this thing also. And and what we're doing here, just taking this xt and subtracting it, this will subtract the noise, and this subtraction of noise is actually this subtraction of noise is actually moving we are moving in the direction where our data lies. So we are subtracting noise, which is removing the part removing the part from the image which does not move us towards the which will not lead towards the our real data manifold. So this, when you subtract the noise from this image, some our each pixel value will move towards the direction where our real data from this distribution lies. So we're just removing noise and going to that direction where our data manifolds lies. And after that, this for loop, we're gonna go this end until we're gonna go from t to capital T to 1, and after this we're gonna return the sample x0. And this will, if our model is trained well, we're gonna go get the sample from the distribution q of x zeros. And what this actually signify that this we are this epsilon theta, this epsilon theta is actually the scaled version of this grad. So I can just, this is a scale version of this quantity. This is a scale version of this quantity. This is some scalar times grad of this quantity, grad x of log of p of x. So this is not some, this is a gradient sign. So this is actually a score function. So we were taking this gradient with respect to x in this quantity. So which is, and this quantity is actually this quantity is called score function. Score function. So what is a score function? Let's look at it. So score function. So if I can, so this is the paper. So for any continuous differentiable probability density p of x, we call grad nebula x log px is its score functions. In many situations, the score function is easier to model than estimate the original probability density function p of x. So this is easier to model in some case. For example, for an unnormalized density, it does not depends on the partition functions. So which is difficult to calculate. So this partition function, and once the score function is known, we can employ Langevin dynamics to sample from the corresponding distributions given a step size. Given a step size alpha greater than 0, or total number of iteration t, and an initial sample x0 from any prior distribution phi x. So prior distribution phi x, Langevin dynamics iteratively evaluate the following and it will sample. This is a sampling technique. So nothing but this is, so we're also gonna go look at this Langevin dynamics. So if we, and this is the description of this quantity, and this is this. So what this signify, this quantity, what this signifies? So this signify that actually, so if you consider this in a two-dimensional space, so this quantity is, if you are in some this p of x, so consider that p of x. some the density. So this is the some two-dimensional density. So we'll have some sort of this thing, the distribution, and we are this is not a this is just a data distribution of one-dimensional data distribution, two-dimensional distribution. So this is our x, and this quantity is actually the vector, isn't it? Set a vector which will point towards the towards the direction which where our maximum data where our the probability is maximum. So b of x is maximum. So if we take this gradient, and it will give some set of vectors, and like this in this case it will give this vector, and it will move this vector towards the point where the probability of getting this data is higher. So you can see here there is high probability than here. So we there is higher probability, so it will give set of vectors, and this x is a high dimensional vector, so it can have the high dimensional, and it will give the direction where to move. And this is actually the this epsilon theta. This epsilon theta is actually saying that this epsilon theta will saying that move the this move the move my current image. So it will just subtract the it. So we will just moving from this xt to the more subtracting with this quantity, and we are moving closer to the real the distribution where from where our real sample lies. So we are actually moving towards this space where this quantity here just signify that move me towards the direction where the max where my data fall within the distribution p of x. So this is the intuition behind the sampling, and this sampling is actually called. So we were sampling from this. So for sampling from this distribution, we call this. So if I show here, so so once score function is known, once we find this score function, we can employ this Langevin dynamics to sample. So from the corresponding distribution. So overall thing here, this overall thing here is called Langevin sampling. So this is a sampling technique from the score function. So this is a sampling technique. So this is Langevin sampling technique. So this Langevin sampling technique, and this is the correct way to sample from this score function. So as written here. So from this p of x, so we can sample using this Langevin dynamics, Langevin sampling, and we're gonna if you do from t1 to t from capital T to 1, we'll actually get. So we'll actually move towards the directions where our data actually lies. So this is actually, if I can show here in this, so in much more detailed way. So I think your data is in a high dimensional space. Your data lie in some sort of high dimensional space, and you start from here. So this is random noise, and you can be just here and just anywhere. So and you are just moving in direction. So we are just making this direction and going back to the original manifold where our data lies. So in high dimensional space, our data doesn't like everywhere. So we have to go to the certain manifolds in this distribution, and we'll find the samples. So from this random space, we are going back into this track where our data falls. So this is high dimensional, and it is even hard to visualize it. And this is the intuition behind this epsilon theta. And if we predict the noise added at this time step t, we can remove the noise and get less noisy image. So if we predict this, so this if we minimize this quantity, we're gonna make this epsilon theta better at predicting this epsilon better at predicting noise, and we'll use this noise predictor to predict noise and remove noise and get better sample iteratively. So and we're gonna go just sam we're just going to evaluate the noise at that time step. So we are not going to how up to which the noise is added, we're not going to track that, but how much noise is added at that time step. So we're gonna go predict the noise and we're gonna subtract the noise and we'll get the less noisy image, which remove the noise at this time step t. So and we will gonna go from we'll go from t to capital T to 1, so we will not gonna go randomly uh, at the middle, so we can't just compute without computing uh, without computing up to t minus 1, we can't go to t. So as you go from in further process we can go to t xt given this x0, but in this model we can't go from x, we have to go to xt minus 1, we have to go to xt minus 1 to get xt, so that this is we can't do this, we doesn't have the solution for that because it's such a robust process, such a complex process. So and we have, this is not a fixed process, this is actually a fixed process, so we can pre-calculate this in a closed form. So and we're gonna go sample we go in this loop, this inner loop, and we'll sample some noise until our time step is greater than t, and so we are not the last step of we are not in the last step, so this is the last step and we are until we are on the last step, so last step of the remove addition, so that so this is x1, so we're not gonna add the noise, we're not gonna sample this when x is equal to 1 and we want to go from x1 to x0, we will not gonna go sample this noise, this inside this loop we will not gonna go sample this noise, and otherwise we will gonna go sample it, and this xt minus 1 is actually, so this is your this is your xt minus, and this is your epsilon theta xt, and we are just giving this image and the time step and we are just scaling it with some factors, so and we're adding Gaussian noise if we are not in the final time step. And what this actually signify that this we are this is this epsilon theta, this epsilon theta is actually the scaled version of this grad, so I can just, this is a scale version of this quantity, this is a scale version of this quantity, this is some scalar times grad of this quantity, grad x of log of p of x. So this is not some, this is a gradient sign, so this is actually a score function, so we were taking this gradient with respect to x in this quantity, so which is, and this quantity is actually this quantity is called score function, score function. So what is a score function, let's look at it. So score function, so if I can, so this is the paper, so for any continuous differentiable probability density p of x, we call grad nebula x log px is its score functions. In many situations the score function is easier to model than estimate the original probability density function p of x, so this is easier to model in some case. For example, for an unnormalized density it does not depends on the partition functions, so which is difficult to calculate, so this partition function, and once the score function is known we can employ Langevin dynamics to sample from the corresponding distributions given a step size, given a step size alpha greater than 0 or total number of iteration t, and an initial sample x0 from any prior distribution phi x, star prior distribution phi x, and Langevin dynamics iteratively evaluate the following and it will sample. This is a sampling technique, so nothing but this is, so we're also gonna go look at this Langevin dynamics. So if we, and this is the description of this quantity, and this is this, so what this signify, this quantity, what this signifies, so this signify that actually So if you consider this in a two-dimensional space, so this quantity is, if you are in some this p of x, so you consider that p of x as some the density, so this is the some two-dimensional density. So we'll have some sort of this thing, the distribution, and we are, this is not a, this is just a data distribution of one-dimensional data distribution, two-dimensional distribution. So this is our x, and this quantity is actually the vector, isn't it? Set a vector which will point towards the towards the direction which where our maximum data, where our the probability is maximum. So b of x is maximum. So if we take this gradient, it will give some set of vectors, and like this, in this case it will give this vector, and it will move this vector towards the point where the probability of getting this data is higher. So you can see here there is high probability than here. So we, there is higher probability, so it will give set of vectors, and this x is a high dimensional vector, so it can have the high dimensional, and it will give the direction where to move. And this is actually the, this epsilon theta, this epsilon theta is actually saying that, this epsilon theta will saying that move the this move the move my current image. So it will just subtract the it, so we will just moving from this xt to the more, subtracting with this quantity, and we are moving closer to the real, the distribution where from where our real sample lies. So we are actually moving towards this space where this quantity here just signify that move me towards the direction where the max, where my data fall within the distribution p of x. So this is the intuition behind the sampling, and this sampling is actually called, so we were sampling from this, so for sampling from this distribution we call this, so if I show here, so so once score function is known, once we find this score function, we can employ this Langevin dynamics to sample, so from the corresponding distribution. So this overall thing here, this overall thing here is called Langevin sampling. So this is a sampling technique from the score function. So this is a sampling technique. So this is Langevin sampling technique. So this Langevin sampling technique, and this is the correct way to sample from this score function. So as written here. So from this p of x, so we can sample using this Langevin dynamics, Langevin sampling, and we're gonna, if you do from t1 to t, from t capital T to 1, we'll actually get, so we'll actually move towards the directions where our data, actually lies. So this is actually, if I can show here in this, so in much more detailed way. So I think your data is in a high dimensional space, your data lie in some sort of high dimensional space, and you start from here. So this is random noise, and you can be just here and just anywhere. So, and you are just moving in direction. So we are just making this direction and going back to the original manifold where our data lies. So in high dimensional space, our data doesn't like everywhere. So we have to go to the certain manifolds in this distribution, and we'll find the samples. So from this random space, we are going back into this track where where our data falls. So this is high dimensional, and it is even hard to visualize it. And this is the intuition behind this epsilon theta, and if we predict the noise added at this time step t, we can remove the noise and get less noisy image. So if you predict this, so this, if you minimize this quantity, we're gonna make this epsilon theta better at predicting this epsilon, better at predicting noise, and we'll use this noise predictor to predict noise and remove noise and get better sample iteratively. So, and we're gonna go just sam we're just going to evaluate the noise at that time step. So we are not going to how up to which The noise added, we're not gonna go track that, but how much noise is added at that test that time step. So this is our approach. And let's look at the implementation part. So for the implementation, we need these things. Unit architecture, we have to understand this. What is unit architecture? Sinusoidal embeddings, attention block, residual block, and these are the things we need to understand. So let's understand the unit first. So unit. So if I can just remove it, it's okay. So it does I doesn't have to remove it. So I've already do once time. So I have written here. So I will gonna go if it doesn't understand this handwriting here. So doesn't okay. So I will gonna go explain you. So this is the reconstruction. So we gonna go. This model is called unit. So this is in the shape of U. So this is unit, and the the input shape is actually the same shape as the out. It has the same shape as the output. So input and output has the same shape, and this arrow. This is this quantity here, and this is copy and crop. So this is also called skip connection. Copy and so we're gonna copy and crop it, and this is off sampling. It's off sampling. Op con 2 comma 2 2 2 cross 2. So and this is max pooling. This is con 1 cross 1. And so we first of all we have a image, we downsample it in some small Latin representations, which is called also called bottleneck, or and which contain the detail deeper representation. And we gonna from this detailed small representations, so we have done some sort of dimensional reduction, and from this less dimension we're gonna reconstructs. And while reconstructing is also called upsampling. So this is not a traditional autoencoder reconstruction. So this is a little bit of a smart reconstruction. So from this small dimension we are reconstructing it in the sequence, but with the help of this deeper representation, this Latin representation, and the time steps at the downsampling. So if we are building this, we're gonna use this and this to build this one, this here, this image. So and for this image, we're gonna go using this representations, which come from this detailed representation bottleneck, and we're gonna go using this quantity and this quantity, which also this is have shallow. This is we call that shallow representation, which is not deeper representation. And so my I can just this is a shallow representation. So if I can, so this is shallow representation. So shallow representation, and this is deeper representation. So from here we are getting much more detail and much more deeper representation, and this is shallow representation. And with this, with the help of this deeper representations which come from here, and this shallow representations in our downsampling means we are doing. So we are just from high dimension we are going to the low dimension. So this is called downsampling, and we are going to using this and this to construct this here. And we will gonna go skip connections helps to reconstruct better images. And we're gonna so this is particularly used in the case where our input is input have the same size as the output, such as in case of segmentation. And this is so we take the image and we go down sample it and up sample it using from this deeper representation and this shallow representation, and we're gonna go get the same output as the input. And this is a reconstruction actually. And and let's understand some of the architecture detail, what they have mentioned. So this is the architecture they have mentioned it. So I have taken it from this guy, Peter Peter Abel, I think. So this is the slide I have taken. So and so let's understand the architecture. So so this is the backbone of Pixel CNN Plus, so which use so we're gonna use unit based on wide resonance. So we're gonna using this unit, and we're gonna go replace this weight normalization with a group normalization to to make implementation simpler. They are using this technique of normalization, group normalizations, and they're gonna go. So their model use four feature map resolution. So from 32 to 4, if you so they are going from 32 to 4 using four feature map resolution, and they are going from this to 4 cross 4 using six feature map resolution, and all the model have two convolution residual block for resolution level and self attention block at 16 cross 16 resolution, and between the between the convolution block. So in 16 cross 16 we have self attention doing some sort of visual attention tasks which is necessary, which will do some complicated processing there, uh, which makes our model to capture much more deeper representations. And we gonna go represent this times to diffusion time. So this is a diffusion time. It is specified by high dimensional, which it will have some sort of dimensionality, and we're gonna be using this transformer sinusoidal embeddings into each residual block. And this is have the not that we just gonna use one number, so we're not gonna use this. We're not gonna give this one two times step as this. So we're gonna go for the time step. We're gonna use this transformer sinusoidal positional embedding, and they have this original implementation model has been trained on this CFAR10 model. The CFAR10 model was trained on this million parameter, and this on this model Lucene, and this is a bedroom dataset, and this is a self face dataset. So they have this many million parameters, and they have also trained a larger variant of bedroom model with the capacity by increasing the filter count. So this is the architecture overview. And what is positional embedding? So positional embedding. So so sinusoidal positional encoding is a method that add position encoding to the embedding. So this is not we need. So embedding to each diffusion step. So this is from this transformer. So this is taking the encoder and decoder part, but it will is a method that add positional encoding to the embedding of our image. So and it uses sinusoidal sine and cos function here. So it will gonna use sine and cos function to represent. This will represent the mm, per they will gonna go it uses sinusoidal function with different frequency to encode the position of each element in a sequence. Sine and cosine are used. Sine is used for even even position. So even position means two four like this, and for the odd we're gonna be using this formula to calculate the position. So this is the odd. So odd. This is the formula to calculate the position using this, and it will give us a this embedding time step embedding T embedding. So we'll call this as a T embedding, which will have some it will have the property. So sinusoid embedding have some property. It has bounded values within certain range, and it is continuous, which is needed. And because for the deep learning model, so we need continuous values. So it work better. So and our value will come from the continuous function. So and which will be sine and cosine, and our value will have the some context of relative positioning. Time step from time step 100 to 200 as in for the relative position. So there is also some sort of relative positioning encode relative positioning feature in the sinusoidal embedding. And this will gonna go actually this is just a representing time step in which time step we are at the diffusion model. So and we have attention block here. So we have attention block here. So what this attention block will do is if you have some images of high like If you have images of some channels, so if you have this first channel and this is second channel and this is third channel, so if you have some images of this channel, and if you just take some of, if you apply this also some attention, visual attention here, it will gonna go focus attend on some part. So this is our attention, you can just imagine it like this. And if you apply this into this 3D 3D boxes, so if you just gonna apply this here, so it will gonna focus on certain patches of images and it will gonna go attend there, and based on that it will gonna go do some prediction here, and it will be learn over time, which help in the predictions. So it will gonna focus on certain patches, and which patches helps to generate what output it will learn from here. Attention block and residual block is basic component of the ResNet. So it will consist of some convolution layer, and after that each convolution is residual blocks will gonna convolute some convolution, ReLU, and batch normalization, not batch but group normalization. And we're gonna see later on this residual block in our code implementations. And this is the implementation. This is some of the idea we need while going to the code part. Let's dive into the code part. So I'm going to using this block, invoicing diffusion probabilistic model, and this code here is resemble the actual implementation. So I'm going to be using this block to explain you the implementation part, and I'm just opening it into the Colab notebook. So, and what I'm doing here, just we have already learned the training algorithm and sampling algorithm, and this is our steps to what you're gonna go do. So there is some description written here, so which I'm gonna go read it out, which is needed in our process. And so if I can, so this is, so we need to define a model that takes two inputs. So we have to define a model that takes two input, the image and the randomly sampled time step. At each training steps, we perform the following operation to train our model. So we're gonna go sample, we're gonna go samples noise to be added to the input, and apply the forward process to diffuse the input with the sample noise. And our model will take this noisy sample as input and output the noise prediction for each time step. And after that, given a true noise and predicted noise, we calculate the loss, and then we then calculate the gradient and update the model weights. So this is the approach we're gonna be taking here in this code. So so we have already also read it. So this is the setup of this ddpm implementation, and the setup is, so we are just importing some of the library here. So math, numpy, matplotlib, tensorflow, and also keras, and we are just downloading this TensorFlow dataset here as DFDS and layers. And this is simple part. So these are the hyperparameter we need. So batch size of this epoch. So this is just for demonstration purpose. So, and this is 100 time step. So time step we are taking as 100. This is a forward and reverse time step. So we're gonna proceed. We're gonna go proceed in 100 time steps. So while back also, while forward also. So this is the time step. So capital T will be here 100. In our example case, the capital T xt will be the 100 x 100, and this is the number of groups in group normalization layer, and this is our learning rate. And after that, this is the image size and channel, and this is the value we are clipping for the pixel values between this bound. Uh, which we want to bound this value within this. So, and first convolution channel will be 64, and channel multiplier will be this, and So what I doing here, just just getting this list, and you are just we are just multiplying this with this each element of this, and we're gonna go this with which is a feature map. Actually, the feature, so in convolution will is work as a feature. So this feature means, so how many channels do you have in each convolution filters, and attention we are going to applying here to attention here in number of res block, number of residual blocks, number of res block is equal to 2, and we are going to be using this oxpot flower data set. So they are given here. So this is the oxpot data set. So this is the flower. So this has been generated by this model. So after that, so we are loading the data set here. So as you can see, we're loading this data set and doing augmentation just left and right randomly within this TensorFlow and rescaling it, rescaling and resize and rescaling. So you're just taking height, width, and this crop size of the image, and just getting this image from this method, crop to bounding box, and so just further doing resizing here into the desired size we need, and just rescaling it within -1 to 1 range, and pre-processing this method will do both possibly it will do resize and rescale and do augmentation and return the images. So we are first of all applying this DDS is our dataset, so we are applying this method, and we are just batching it and shuffling it and prefetching for the training. And if you just this is Gaussian, we define the forward and reverse process as a separate utility. Most of the code in this utility has been borrowed from the original implementation with some slight modification. So this is the arguments of beta start, beta end, time steps, and this value is the order defining here. So and this will and we are just again initializing this with this self method, so we can use later on. So this is and defining this linear variance schedule. So what we have already studied, this linear variance schedule. This actually beta values. And so beta and beta line shift. So we are trying from 0 point something, not this is from 0.00. So this value to is, so this is -4 means we are going from 0.001 to this here, this value. So we are this is a linear, so from the beta start to beta end, so we're gonna go forward and create this linear variance schedule, and after that number of time step will be int of time step. So time step will be we're gonna be passing it and saving it, and this beta is actually 1 minus 1 minus alpha is 1 minus beta, and this beta is not such a, this is a set of vectors. So this is we're minusing each vector here and applying this comp product, and this is the previous, so just previous of this. So alpha t minus 1, so this is alpha t, alpha bar t, and this is alpha bar t minus 1, and it's just again defining the same thing, constant, and changing the data type. We're nothing doing here. So this as a constant and doing this calculation. This is a forward process, guys. So we want to give less noisy image. So what are doing here, just giving less noisy image and predicting, giving this giving this less noisy image and getting this more noisy image. And we are defining here this square root of, for this calculations we have already understand that for this calculation we are defining this square root of alpha bar t and square root of 1 minus alpha bar t, square root of 1 minus alpha bar t. This complex product, and this comp product will just like it will just do operation. This comp product will do, if you have the setup number, so it will take this first number is first number, and then second number they multiply first and second and go in that fashion. So and this is a log 1 minus log 1 minus alpha com product, and this is a just doing they are just doing some calculations here. So and this is a reciprocals of alpha bar t, and which we're going to apply later on. So this is the reciprocal of 1 minus alpha com product. So and this is the and this is actual reverse transition, but we doesn't have to access it. But this is thing will be useful by when training the model. So we are calculating this q of xt given this is track when we are condition on x0, it is tractable, and it is also Gaussian. So we are defining this posterior variance here using our formula which we have read. So posterior variance formula we're using here. So if I can, so ddpm papers, ddpm papers, if I can show you calculating this posterior variance. So, so what is our posterior variance? So this is the posterior variance. So yeah, so this is the posterior mean. So this beta tilt is the beta tilt this and beta tilt and mu tilt are the posterior parameters, posterior distribution parameter, and so the forward posterior mean. So this is forward posterior mean, and this is a forward posterior noise noise addition term. So this is also is variance. So this is posterior variance. Posterior means as x q x t minus 1 given x t. So that's the posterior, and let's go into the other part there. So mm, so log calculation, because we are calculating this posterior variance, so we are just calculating this uh, posterior variance using this formula, and we are calculating this posterior variance and just changing the data type for better numerical precisions. And log calculation, so log calculation are clipped because the posterior variance is zero at the beginning of the diffusion chain. So we are if you are taking log, so log of zero is undefined, so this calculation will stop. So we are just clipping it using log calculation clip because the posterior variance is can be zero, isn't it? So at the beginning. So and this posterior mean coefficients 1 and posterior mean coefficient 2, these are the parameters for this posterior distribution which we're gonna need. uh, this is the coefficient. So what they have used, I think here, I think something they are what they are defining here. So this is beta times np of square root of alpha bar t minus 1 and divided by 1 minus alpha bar t. So this is the posterior calculations which can be used later on. So and this is the second coefficients, means the coefficient means just above term of the variable. So what the main thing, so this is the posterior we need, and this extract method will just extract some of these things. So extract some coefficient at a specified time step. So this method we are defining here, and a is a tensor to extract from. So a is a tensor to extract from, and t is for which time step the coefficient are to be extracted, and accept the shape of the current batch samples. Shape of the current batch samples, and extract some coefficient. So then reshape it to this for broadcasting purpose. So what are doing here? This is also gather it. So it will just give gather means we are going to go applying this gather method, which will I think it's possible it will take we are going taking this batch size, and this will actually do um, so it will at specified time step it will get our this um, it will actually get the coefficient. This gather method will actually get give us the coefficient at the specified time step t. So and we are just reshaping it for the broadcasting purpose, and this is a q mean variance. So q mean variance and extract the mean and the variance at the current time step. So and this is x star the initial sample before the first diffusion steps and t the current time step, and we are taking this shape. So just we are taking this shape, and for we are taking the at the this value current time step. So this is the shape and we are multiplying this is the mean and this is the variance, and this method will actually give us the mean and the variance at that current time steps, and this will return mean variance and log variance. And I think we're using log variance for stability, I think numerical stability. So and this method, this q sample will actually we're starting with self xt and giving these parameters here 1 2 3 4 parameters, and this will diffuse the data, and we're gonna go initial sample. So before the first diffusion steps, so it will just give the first start initial sample, and will this is the current time step, and this is Gaussian noise to be added at that current time step, and it will return the sample at time step t. So first from the first x0 we can get this. So this is q of x0 given x so q of xt given x0. So this is the thing, and this is the x start shape, and this will be taking shape, and it will extract something. So here what will it extract this at a particular time step. It will gonna give this quantity here, this quantity at the particular time steps, and we are multiplying it by this. This is a formula, actually the formula of q of xt. So this is the first. So this will be square root of alpha bar t, and it will give at that particular time step, and multiplying with x0, and it will again give us this square root of 1 minus alpha bar t, and we will gonna multiply this with noise. So this is actually the formula, if you can remember. So I can show you. So this is the formula. So this is such a simple formula they are applying here. So this is the formula, I think they are just for time step t they are just. So this is alpha bar t x0 plus root over of 1 minus alpha bar t into noise. So they are just implementing this formula here, and this noise is epsilon here, and they will noise from predict start from noise. So they will gonna predict this start from the noise. So they will gonna go give this xt, arbitrary xt, t and noise, and also we are, and after that we're gonna go get this. First we're going to take the shape, and we're gonna go return this. So this is actually the method. So this is 1 by square root of reciprocal of alpha bar t. So this is this, and we are just taking at this value, taking at this time step, and just giving the shape, and multiply with this xt, and this is self dot extract of self dot square root of reciprocal 1 minus square product times t into xt, so shape into noise. So I think at that this is the. So this is the predict start from noise. So this is actually a sampling process. If you observe it, so this is first of all we are 1 by this, if I can show you. So this is so 1 by root over of alpha bar t, and we are just giving it. So this will be and time step and this will be extended, and to giving t and xt and into multiply by noise. It will give the x0 from noise, and this is the q posterior. So compute the mean and the variance of the diffusion posterior. So this will be q of x. This is the above method. So this is the posterior. Compute the mean and the variance of this posterior, and this which is condition on x0. And this is x start, xt, and the current time step, and it will return the posterior mean and variance. So just taking shape and just doing the applying the formula which for the first the posterior mean, and this formula has been given in some paper also. So if I can show you the posterior mean formula. So this is the posterior mean formula, and this is the posterior variance formula. So this is the formula I want to show you. So this is the formula they are applying, and they are applying this. This is called posterior. So there is something called tilt in, if you have the mu tilt t and mu beta Thirty tilt, this is the posterior, you can understand it. And they're applying the formula here. So for the posterior mean calculation and posterior variance calculation, and they're also calculating this log clip too. So they are using this, they are not just applying the log variance, so they are taking log variance and they are returning it this three quantities. And we are using clip so that log domains, so log will, so we doesn't have to put zeros in the logs, and which is undefined. So if we have to clip when we are using log variance. So and this will give the p mean variance. So p mean variance means our just a model. So this is a model. So so p mean variance, and it will x dot reconstruct self dot predict start from noise, and we're gonna go this x t time step and noise actual noise is equal to noise predict. So and what are doing here? So clipped, if clipped is equal to denoise true, then we're gonna go so we're gonna go. So x dot reconstruct is equal to t dot clip by value. So reconstruct self dot. So we're defining this, and after that, this will return model mean. So model mean and model variance and posterior log variance from this q posterior. From this method, we will gonna get this value. So model mean, posterior variance, and posterior log variance, and this is our x start is this here, and this xt will be our x. So we're gonna go understand it when you call this method, and we're gonna go analyze it, and we're passing this time step. So it will gonna predict the less noisy image given the more noisy image. So it will gonna go do some. So we're passing here noise pattern. When you call this method, we're gonna go see it. That is the sampling algorithm. So this is what I have already written. So p sample. So we're passing this spread noise xt and clip denoise is equal to true. So passing this time step and t sample from a diffusion model. So predict noise. So the noise predicted by the model, the sample at the given time step for which the noise was predicted, sample at a given time step. So this is the not this pure image. So this is the image at a given time step for which the noise was predicted, and this is the current time step, and this is the whether to clip the predicted noise within the specific range or not. So this is a bool value. So and model mean, model log variance we are taking here. So from this method, so what you're defining here, this is a p mean variance. So we are so from we're calling p dot mean variance. So p dot mean variance here. This method we are passing, and what are predict what are sending here. This spread noise. We're passing the spread noise in this method the p sample, and we are passing this x and t times step t, and we are just giving this boolean value here, and we're sampling some random noise, some no Gaussian noise, and so no noise at t is equal to 0. So if you are at the final step of the final step of the reverse diffusion step, so we will not gonna go add the Gaussian noise, and we will not want to be within the distribution for the further processing of epsilon t calculations. So yes, so for the line last time, so we will not gonna go add this z. So this noise sample from here we will not gonna go add here, and we will, because at the last sample it doesn't want the noise sample. We add the noise sample because in the reverse process we add when sampling we sample and add Gaussian noise, little bit of Gaussian noise, not as that much, to within to make the alpha theta, the epsilon theta calculation within distributions, which helps to go backward in the reverse direction of the forward processes. So and this is the, and we are returning the mean and the this quantity here. So return. So this method, this p sample will actually return this quantity. So mean plus this non-max, this here non-max into tf dot expo, the tf dot exponent. So we are using this exponential functions, and it will multiply this and this model log variance, and we're going to multiply it, and we're going to go return the samples. So here, and this network architecture is unit original development segment. Semantic segmentation is an architecture that is widely used for implementing diffusion model, but with some slight modifications. The network out a step to input in image and time step and self attention between the convolution. Once we reach the specific resolution 16 cross 16, and then group normalization instead of weight normalization, we implement the most of the things as used in the original paper. But and the activation function, we're gonna use this switch activation function, and we're gonna go using and use the variance scaling kernel initializers. So this is our kernel initializers for the variance scaling, and only the difference here is the number of group used for the group normalization layer. This is the difference. So they have used, I think, 8, and the original paper have used something much more than that. So they are using this group normalization, and default as they have used 32. Dropout is optional and should be used where the chance of overfitting is high. In the paper, the author use dropouts only when training on C14. So they are using when they are training C14, but we are not. We are using Oxford Cloud dataset. So and this kernel initializer function is designed. This function what it actually does. This is designed to create a skill variance initializer for the model layers and ensuring that the training is started with the appropriate initial value for the weights, contributing to the better convergence and the performance of the DDPM models. And so these are the function of this method, and this skill will this control the variance of the distribution used for initializing the weights. In this case, it is passed the skill value determined by the functions, and after that this they are giving some parameter also. So and distribution, so uniform. So I have just pasted out some of the some of the things. So if you can just read it, and this is the attention block. So attention block, and this apply self attention here, and unit is the number of units in the dense layer, and the group number of group to be used for the group organization layer. And what we're doing here is just uh, passing this units, and the group is equal to it, and this quark, and the self dot unit is equal to unit group dot group, and this norm was just initializing some of the layers. So this is layer, no, layer, and this is the dense and dense. So this is for projection, this is for value vector, query vector, value key. And so if you have read the attention mechanism, so these are three types of vectors. So we need, so for the self attention mechanisms, and this will gonna go create helps us to create in natural language processing. It will help us to create some context aware embeddings. So and in the case, in the visual attention, we use in a little bit of different way than sequence. So we need the query key and value vectors, and we're gonna go passing. This is also be a dense layer, dense dense. We are just initializing the units here, and they're just giving this just linear for the linear projections also. And they first of all we are gonna this when you call this method. So and it will take some batch size. Here the batch size, height, width, and scale, and then this input will be. So first of all we go to the so we're gonna go take this input as a normalized input. So and we're gonna take this query vector, key vector, and this value vector, and we're going to calculate this using this Einstein. This is something called this Einstein summations, and this is actually doing the this is a query and key. So this query vector, if you have something like if you have image, and image have some properties, and this is query. So this image is just asking certain part of this how much you are we are similar. So this is a similarity. So if I can just show you here, this query and key vector are asking the similarity between them. uh, if I can show here. So this is the so this is what this sum is what I'm doing here. So this stand for Einstein summation for a powerful function in TensorFlow that perform operation on tensor multidimensionally using a notation that generalizes matrix multiplication element wise. So we are gonna go do element wise operation, and this is actually a dot product between these vectors, these two vectors. So and we are gonna go doing element wise as we do in the dot product. And this is a query tensor in attention mechanism, key tensor in attention mechanism, and this ensure that So specify how tensor should be multiplied and how the resulting. So we're gonna apply this and we're gonna get this shape after this operation, this and some operations. We're gonna get some resulting tensor of this shape. And let's break down this with notation. And they have just given this pass size, and this is the attention head. And if they are we are using multi-head attention, then this actually give this value, and this is the width of the special dimension in the query tensor, and this is the channel in the query tensors. This is the width of the special dimension in the query tensor, and this SW2 of the special dimension. So this is the image, so special dimension in the key tensor. So this is the height and width of the key tensor, so dimension in the key tensor, and this operations perform. So this is a query and key, and they have this same. And if you do the dot product between these two vectors, the operation compute the dot product between the query and the key vectors across the channel dimension C. So this is the channel dimension C, and especially for every locations, it calculates the similarity with key location. This by taking the dot product of their corresponding channel vector, the resulting tensor has a shape this, where each element in the SW corresponds to a similarity score between the query at that location and all the key square. So this is also similarity calculation. So similarity score between the query tensor at the all query at all location at that location and all the keys across the special dimension SW. So this is actually a similarity. They are doing some attention mechanism here. So this we will have to finally we get this tensor, and here this SW, this after that calculation, this SW is such an important quantity. So and which correspond to the similarity score between the query at that location and the all key score at across the special dimension. This so this will kind of calculate the similarity scores for our model. And after that, the result of the shape, this is the shape of this that contain the similarity attention score between each query position and all key positions. And the attention scores are received into 2D matrix for the shape. So I have added this documentation for the explanation to you, and you can also reference out when you need. So attention score are received into 2D matrix of shape this, and we are just flattening. So this function will actually do, we get this shape, we obtain this shape, and we're gonna flatten this by multiplying these two last elements, and the softmax, and this will just do flattening. So and softmax function is applied along the last dimensions to normalize the attention scores. This convert the raw similarity score into probability. So from we get some random values, but indicating not bound value between 0 and 1. So if you apply the softmax, you will get some bound values. And attention score are received back into the original 4D shape, this shape, and the format is necessary for the next steps, where the attention score are used. So this attention score are used for doing weighted sum with the value vectors, which is the last step. I think last step to create some last step to create contextual embedding in case of this attention mechanism, and they're just reshaping it. So this format is necessary. So what are we doing again, we are reshaping back to the original 4D shape, this shape. And after that, this is format is necessary for the next step, where the attention score are used to weight the value v vector weight tensor, and we are just reshaping it to our desired shape for the upcoming calculations. And here again doing some calculations here. So we're doing weighted sum between these two vector and getting from this shape, see this dimension, this and this have this dimension and this have this dimension, and getting this shape. And this is a final. So and I just want to tell you again one thing. So for each query vector, this for each query position as W, it compute the weighted sum of the value at all the key position. This and resulting in the projection tensor pros of shape. This essentially the model compute the new feature representation for each position in the input by attending to all other position in the image based on the attention score. So based on the attention score, it will focus on particular part of the image. So if the attention score is high, it will gonna focus much more on that part. So this is use of the attention here applying here. So if the attention score is high at certain part, so model will gonna focus on that part while generating or predicting samples. So it will do some sort of complex processing here, and this is a finally it is applied to the output of the attention mechanisms. This step is typically in attention layer where the output is linearly transformed before it being passed to the next layer. So we'll use some linear projection here using this linear process, which is also a dense layer. And after that, we're gonna go add this final, and we're gonna go do some addition during the projection. Projection means the original input is added to the projected attention output, and this will actually this function, this call function will give this attention call function will give this transform embedding with which return this, which also add the part also. And for the time step, for the time embedding, so we are defining this dimension. So as I have discussed in the sinusoidal embedding, so we are just giving this dimension, half dimension, and this is just a parameter which you need to calculate this formula here. These are just parameters what I are specifying here for the calculation of this values. So we need these values. So for the calculation, we are just calculating some values here, and this is dimension by 2, and just calculate applying the formula and getting the self dot embeddings. And when we call this method, so we're gonna go cast tf dot cast, and we'll use 432, and we'll multiply this here input, and we'll also multiply this embedding, and we're gonna concatenate this both sinus we're gonna using this both sine and cos for the embedding generation, and it will return this embedding residual block, which has this with this and a group of where we are adding group as 8 and in activation using switch. And this method will here this method we're going to return this apply method, which is this method. So this residual will give us it will give us the residual block for us. So this method will give us this residual one block. And what we're doing here, just taking the input with in this and input time step and t, and if this condition satisfied, we're gonna go add residual as this, and else we're gonna go use this as a residual. And this is the time step time embedding, so we are passing this to the activation function, and then dense linear layer, and applying group normalization activation function and this convolution. So this is one, it's a residual block, and in that residual block we are adding this time step and the image and the time step. After that we're going to go apply group normalizations here. So and after that we're going to apply this activation function again, and again continuity, and you're going to return, and we're going to be adding this x and residuals. So which will come from the another layer. So this is a residual block, and this is a downsampling one. So just defining some continuity with some parameters, this will help in downsampling. So and this we're going to return this apply method, and another this upsampling. So we are using upsampling 2D, and this after that is con 2D, and we're going to return this, which is used for the upsampling of our image. And this is time MLP. So and it will gonna go, and we are returning this apply method. This apply method will what it actually do is take some input, and it will take and this is a time embedding. So time embedding. So so yes, so it will gonna go take this input as times, and it will give us this time embedding, and after that we're gonna go pass this time embedding through this linear layer, dense layer, and we'll get this time embedding and returning this method again. And let's build the model. And this is the parameter of the model, and which has this input and image channel, and this is the time input. So this is the time input, and we are gonna go applying this con2d and we are passing this x after the first convolution operation. We're gonna go pass, and we'll also pass this time input to this time embedding. This is the custom functions, and we're gonna go pass this. After that, we're gonna pass into this MLP, this time embedding. We're gonna pass into this MLP multi-layer perceptron, and then we also gonna keep this x in this skip, and it's a down block which will this we are just running this with. So in this range, we are just creating our down sampling block here, and if our certain I reaches, so if we are we are applying two potential potential, so if I become index 2 and 3, so we have this define here. So here if I show here where we have defined some as attention here, so we are defining here. So if this is true, we gonna go apply this self attention here, otherwise we will not gonna apply this self attention, and we're gonna create this the down sampling block here, down block, and this is the middle block after that. So this is our up block, so this is the reverse of this length of width, and we are gonna creating from this low dimension to the from we're gonna, and if attention if a certain we achieve it, we're gonna go a certain layer we where attention has been applied. If we reach this, we're gonna apply this attention mechanism here again, and mm, if I not is equal to 0, then we're gonna go up, sampling it, and after that this is the end block. So out at the end we're gonna go apply group normalization activation function, and this which will convert into our channel. So these are much more higher channels, so we are just giving this filter as 3, so it's make 3 channel for the color images, and returning this model. And the training is pretty simple here. So for the training, we are just defining giving this EMA network. So this is I think it's exponentially moving average on the model parameter. So with the decay of this, so we are gonna go this work better as in this diffusion model, and we're gonna be using Adam with learning rate. This we will gonna go use EMA on model parameter with a decay of factor of this, and this will take this many parameters. So network, EMA network, time step, and GDF utils and EMA. And this method we're gonna go get the batches of get the batch size. It's our training method. So first we're gonna get the batch size, and just we're gonna sample uniformly our time step, arbitrary time step. So this in forward process we're gonna sample other twice, and sample noise to be added to the image in the batch. Sampling noise to this is different noise, and this is different noise, guys. They will this is not noise, so this is time step, sampling time step, and this is where we are sampling noise, which is a Gaussian noise, and we are going to diffuse with this noise and pass this diffuse image and the time step. So pass the diffuse image and the times to the network, and this network we're gonna passing through this network, and this will and we're gonna calculate this loss between this model predicted output, and this we're going to calculate this loss, and this using this tape gradient loss, we're going to compute the gradient here and up. And what we're going to do, we're going to go in all trainable parameter, we're going to go apply this gradient updation. So after that, update the weights value for the network with EMA weights. So this is for the exponential moving average, I think, EMA net weights. And here we're updating the weight for the EMA model, and after that returning loss, and this will generate samples. So this is a randomly sample. So this is a sampling starting from starting point for the reverse process, and sample time step sample from the model iteratively. So this is the iterative process. So from we are in a reverse, so self 0 to self theta time step. So this will be 1000 in our case, and we are giving this batch size as this number of images, and after that we're gonna go apply this method p sample, and we're gonna go sample it, and we're gonna return the samples. So after that we're gonna go plot. This is a method for utility to plot the images using the diffusion during training. So it will gonna this method, we're gonna go create some subplots here, and it will gonna first it will gonna generate the images, and we gonna go, so we gonna go apply this clip by value, and this will to the original image, and this will be converted into numpy with this data type. So this method will generate samples, and after that we're gonna do some pre-processing for the samples to show to visualize, and creating some subplot here, and printing the generated sample here using this method. So and after that axis is equal to off. So and what we're gonna do here, we're gonna go so this again images, and this will gonna give us this tight layout, and we're gonna go show it, and we're gonna go build when we call this method and pass this parameter. This will give us the network model. So and this is gonna go give the EMA network, and we are passing this parameter here, and we are initializing the weights are the initially the weights are same. So we're gonna go add then this network weights. So for the EMA network, the first time it will the network weight and EMA weight will be the same, this model, and this EMA network exponential moving average network, and our network will have the same weight at initially get an instance of the Gaussian diffusion utility. So this is the what we have defined earlier. So this will so what we're passing here this total time step. This will give this instance GDF utils, and which we're gonna use here. And this model will take this networks and in this Gaussian diffusion utils and time step, total time step, and we're gonna compile this model using this losses and optimizers, and this is just passing train data set, defining and also defining this callback. So, so we're defining your callback, and if you just so they have this given this checkpoint, so you can just run it and see your check. This will gonna save the file here, and when you click this, so and when you gonna click this, we're gonna plot this images here. So if I run it, so I have a limit on my GPU. So if it's on, I will show you. So this is the overall idea of the diffusion model, and in the next video we're gonna go deep dive into the improved DTPM and DDIM and the classifier guidance. These are the upcoming topics.